Hello, George Romanic here. Welcome to Fundamentals of Weather and Climate playlist. In today's video we are going to define the normal temperature and what meteorologists mean when they report this value. Normal temperature can be calculated for a day, for a period of a month, year, season, and so on. And it simply represents arithmetic average of 30 years of data. So if you want to calculate it for a particular day, let's say 17 August, then you take 30 years of 17 Augusts and you take daily average temperature for each of these 17 Augusts and you calculate normal temperature by averaging 30 of these values. If you want to calculate normal temperature for the month of August, not particular day, whole month, you take average temperature for 30 Augusts that correspond to 30 years and you calculate arithmetic average. And the same is if you want normal temperature for a year, you average 30 years of data. So one can usually focus on three values: normal minimum temperature, normal maximum temperature, and normal daily temperature. So how is that calculated? Well, if we have a graph here, and let's say, for example, we want to calculate normal minimum temperature, then the y-axis will be minimum temperature, perhaps in degrees Celsius, or Fahrenheit or Kelvin, whatever you want to use, and here is time period. And this time needs to be 30 years, as we said. Now, we will have 30 data points, therefore. I don't know now if I will have 30 dots here. Probably not. But these are 30 points. How is then normal minimum temperature calculated? Well, we take average of these. So this blue line is normal T minimum. So you can see immediately that the next data point, if we want to predict it, is not necessarily going to be on this line, because there are so many points that are not on this line. In fact, in my particular example, there are only 2 points that are on this arithmetic mean line. And it could have happened that there is no points. In other words, that this normal minimum temperature was never actually observed, because it's just mathematical average of 30 points. In my case, though, it was observed 2 times. So if we cannot use this blue line or normal temperature to give prediction for future, how do we use it and what's the purpose? Well, there are 2 things here. Purpose is we get idea of what is climatological mean for this particular weather station over a long period, 30-year period. And 2 is how can we use this to give some information, prediction, what is likely to happen next. To use this value, we have to calculate one more quantity, and that is called standard deviation. Standard deviation measures the spread of these data points around the arithmetic mean. So we calculate standard deviation, and I'll show you how to calculate it, and then we add one standard deviation above this line and one standard deviation below this line. Now you can see that most, not all, but most data points are within plus minus 1 STD. And here STD is standard deviation, not something else. So this is mean plus 1 standard deviation, and this is mean minus plus 1 standard deviation minus 1 standard deviation. It can be demonstrated that if these data points follow the normal or Gaussian distribution, then plus minus 1 standard deviation will contain 68% of all data. Now, this can be used to give some prediction, because I can tell you with 68% certainty that the next data point will be within plus minus 1 standard deviation around normal. And in 68, almost 70% of the cases I will be correct. Not in all cases, because notice this point is outside, this point was outside, this one is outside, this one is outside, this one is outside. Now, it's a decision an expert has to make whether he or she wants to use 1 standard deviation or maybe use plus minus 2 standard deviations to report variability around normal. If one uses 2 standard deviations, then maybe you will you add 1 more standard deviation here and you add 1 more standard deviation here. Let's just remove this, make it even more, put it here. Now, if you take plus minus 2 standard deviations around normal, it can be demonstrated that you will capture 95% of all data in your data set. So I can tell you that with 95% certainty, the next data point will be climatological normal plus minus 2 standard deviations. Not all, 95%, because in this particular case, 1 outlier is still over here. In practical atmospheric science applications, we usually use 1 or 2 standard deviations. In some cases, 3 standard deviations are used. If you add 1 more standard deviation around the normal, then you will capture 99.7% of all data if data follow Gaussian or normal distribution. So this is what normal temperature means, and this is how it is used together with the concept of standard deviation to give prediction of next data point in the time series. Of course, I used here example of minimum temperature, but the same is for maximum temperature or daily mean temperature. And daily mean temperature, as we saw in my previous video, is usually calculated as arithmetic average between maximum and minimum temperature for a given day. Now I would like to discuss quickly how is standard deviation calculated. Let's do it. So if we want to calculate STD for minimum temperature that we had in previous example, then standard deviation is calculated as square root of T minimum in year 1 minus T average. T average on this channel we use T over bar. And then you square this plus T minimum for year 2 minus T average squared plus 3 dots because we have 30 years plus the last year. T minimum for year 30 minus T average squared divided by the number of years, which is 30. That's how you would calculate it on your spreadsheet. This can be written in a more concise way to say that standard deviation is square root. Instead of writing all these pluses, we say it is sum, and we use this Greek letter sum when a counter I, let's say, goes from 1 to maximum 30 of T minimum I, T minimum for that year I minus T average squared divided by N. Divided by 30. This is divided by 30. But usually we also put here to be more general, because sometimes, rarely, sometimes it's not 30 years, So we put here n, and we put here also n, but quite often n is equal 30. So this is more general. If you want 40, then you just put n equal 40 here. Anyways, this is equation for standard deviation. And this formula is the so-called, this is now technical detail, this is a formula for the population of data. There is one technicality. If you want to use sometimes a little bit more accurate formula for the sample, then you would put here -1. So some people have formula with n, some people n-1. In advanced videos on Thursdays, I will explain what the difference is, but for this fundamental playlist, it doesn't matter. The point is you can use formula with n or formula with n-1, just be consistent. And this is how that standard deviation is calculated. Now, as I said in previous slide, if our data follow Gaussian distribution, if they follow normal distribution, then it can be demonstrated that ±1 STD corresponds to 68% of all data, that ±2 STDs corresponds to 95% of the data, and ±3 STDs correspond to 99.7% of all data. So if you give prediction for 2 STDs, you will be correct on average in 95% of the cases. Lastly, let us see example of normals. Here is maximum temperature in degrees of Celsius for the month of August. And it is calculated over this climatological standard of 30 years, which is 1991-2020. Another climatological standard was 1961-1990. In principle, you can use any 30-year period, but in climatological practice, people sat around the green table and agreed that a nice climatological standard is 1991-2020, and before that it was another 30 years, 1961-1990. So you can see here legend, you can see that maximum normals, temperature normals, are higher in the equatorial regions compared to higher latitudes, that here close to equator they are exceeding 35 degrees Celsius, but in high latitudes of northern and southern hemisphere they go to negative values. You can also see that we have much more data in Europe, United States, highly populated regions of Asia and Africa, as well as South America, but over oceans, Antarctica, Arctic, we have very little data points because there are no people there. The same happens over the Sahara Desert and Amazon forest area. There are not that many people, or in other words, there are no many weather stations to record data that are used to calculate this. You can find many other examples online. This is just one example to show you how calculations and analysis that I demonstrated here are actually used in practice. Please make sure to like and subscribe, share these videos with your friends and enemies, and until next video, goodbye.